last satellite event in these 3 days of the Artemis annual meeting, and the last satellite event is devoted to the communication of the project to stakeholders, especially here in Brussels and in Belgium. So we will start the afternoon session with the introduction to Artemis provided by Roald. Please, Roald.
Thank you. So, welcome everyone. So, indeed, we are going to talk today about the ARTEMIS Project, which is a European Horizon Europe project on digital twins, reactive heritage digital twins. So it's one of these projects within the European cloud where you have a number of projects which are destined in order to bring cultural heritage to the digital world and vice versa. And here we are part, Kikirpa is part of this European project where we have 22 partners spread over 12 countries, where we're trying to develop further the aspect of digital twin. A digital twin is a digital replica of the physical object, so you can work on the digital object, try out different things, restoration activities. You can see how it responds to changes in climate, how it could react to other conditions, have an impact of the object, and that's the meaning of this digital twin. And so you see it's reacting to what's happening outside, so there's a purpose of what we are doing, a reactive heritage digital twin that we want to develop. This past 3 days, past 2 days and today, we've had our first annual meeting. The project started the 1st of January of this year, and we held our annual meeting here at Kikirpa. And so I wanted to offer the opportunity to our Belgian partners, our Belgian stakeholders, to present what we are doing on this project and make the use opportunity of the people from our project, the partners of our project who are here today to present you what we are doing, because they can explain it much better than I can do. So I leave the word to them.
Thank you, Roald. Again, special thanks to Kikirpa for hosting the first annual meeting of the project. And as I understand, we start from the most new subject in the list. So with something that cannot be defined because it's better after hearing Franco this morning, large language models usage in Artemis, please. And not only, okay, not only. And ontologies, yes, you're right. I think you need ontologies to use large language models.
We will start from that. Okay, great. Yes, I'm not that tall, but better this way. Hello, thank you all for being here. We will start the presentations with getting you into details, giving you details about the way we exploit ontologies and artificial intelligence methods, together with my collaborators, Miriana Somenzi and Aida Himish from the Ariadne Research Infrastructure, and how we actually use them within the Artemis infrastructure to to build a consistent infrastructure that has a coherent view of the data that we integrate. I will start by giving you the foundation, the semantic foundation, on top of which we then build the artificial intelligence methods and techniques. So I'm sure by now you all know what digital twins are, but let's recap a little bit to say that we have seen the digital twins first coming in the industry. We're very used to these models that actually monitor and predict specific operational and mechanical systems. These systems, when dealing with different kinds of domains, like the cultural heritage domain, are completely different and have some other complexities that we need to deal with. So in cultural heritage, we need to deal with assets, cultural heritage assets that are actually living assets and carry their own meaning. They have a specific history, they have documentation and scientific evidence. So when dealing with cultural heritage assets and digital twins of cultural heritage assets, we need to combine all this information, unite, integrate all this information, and end up to a view, a coherent view, where all this information is related to each other and fits with each other. So in order to produce a heritage digital twin, we cannot just stay to a digital replica as it is with physical systems. We need to go beyond physical replicas, and we need to go towards an understanding of the cultural knowledge as a whole. This is a typical example here, one temple, one monument, one cultural heritage asset that is accompanied by different kinds of information, different kinds of data surrounded. These different kinds of data come from different workflows, from different contexts. They may have different scopes. What they do is they speak a different language. And we need to integrate all this information in order to have one coherent view about the specific asset. We may have different isolated data collections that need to be integrated in order to have one unique view, coherent view about the specific asset. So, what do we want our reactive heritage digital twin, or RHDT, as its abbreviation? What we want it to understand is diverse heritage information that is integrated into one single coherent view. So we need to know how it has been created, how it has been analyzed, how it has been studied, which specific data have been produced, by whom, and how all this data fits together. So we also need to keep track of versions, of workflows, of provenance, and also interpretations. We need to interpret the documentation, we need to interpret the observations and the models that we have about a specific asset. The reactive heritage digital twin has an additional characteristic. We want it also to respond. We want it to be reactive. So we want to have responses to monitored or predicted risks. It is essential. So we want it to be evolving as knowledge arrives from different data and from different sources. This is where ontologies come into play, actually. What is an ontology? I suppose most of you are familiar with the term, but I will have to say the definition that is, it is an explicit specification of a conceptualization. And what does that mean? That it is a description of what we know, the description of knowledge that we have about a specific domain. So how do we achieve that? We actually achieve that by defining classes, which are categories of things that you can find within the domain of discourse, and relationships that exist and relate these classes between them. It is usually formally represented as a directed graph, like the one you can see on the right side of the slide, where the nodes represent the classes and the edges represent the relationships between these classes. Now, there is something good with this structure that is, first of all, understandable by humans. You can easily read it, but it's also machine understandable. So you can exchange information between machines using specific formal languages that are understood by machines and can be interpreted in a unique and coherent way. This is why we have chosen to build the RHDT ontology, the Reactive Heritage Digital Twin ontology. And our ontology needs to take under consideration three different aspects, needs to be developed having three different things in mind to be conceptualized. The first thing is that we needed to be able to describe the world as it is. So tangible and intangible assets, actors, places, primary data, whatever we have around this world. The second aspect has to do with the digital representations. We are in the era of the digital world where we represent everything through digital means. So we needed to be able to describe the world through also 3D content, transformations, and software processes. The third the last but not least aspect is the reactive behavior. We want to also capture the reactive behavior of our RHDTs. So in order to make them reactive, it needs to also describe simulations, what-if scenarios, sensors, and reactions. All these combined produce the RHDT ontology. Of course, we cannot disregard the international standards, and ISO standards have already been built and are used throughout the cultural heritage systems. So our ontology is fully compliant with the CDOC-CRM ISO standard, which means that it is compatible and interoperable with all the systems that use the same standard. We use the same language with all the systems that are CDOC-CRM compatible. On top of that, and of course in line with the linked open data principles, we reuse knowledge that already exists. We do not reinvent the wheel. Whenever a concept or a specific type of knowledge already exists, like in other models, like in the CDOC family of models that you can see on the right side of the slide, we reuse the existing information in order to be compatible with all the other models and contribute to this linked open data world as well. I would also like to add that we also use established heritage vocabularies for defining specific types of assets, for example, like the Getty AAT thesaurus, or for defining specific time periods from the periodo vocabulary, so as to incorporate all this existing knowledge into our models. We have chosen to build our HDTO using specific modules by developing modules in a modular approach. And here you can see at the bottom of this image the common entities that have been that are being used. They mostly come from the CDOC-CRM because this part of the entities includes the actors, the places, the time spans, and so on. All the common entities that exist among different domains of discourse. And on top of them, we have built specific modules, specialized modules, to describe the knowledge that comes from different activities that we are interested in the ARTEMIS project. This is a structure that allows us to be coherent and also extensible, which makes us very flexible if new information arrives and if new knowledge arrives also in the future. The ontology is, of course, expressed in a typical language, in a formal language. We have expressed it in RDFS, which allows us to use and exploit the software tools and the systems that will allow us in the sequel to take advantage of the magic of inference. So, unlocking intelligence, the magic of inference, this is a, let's call it a phrase that I stole from my friend Achille here. So I need to say that. Inference is actually a special characteristic of ontologies that when applied on top of semantic data, it allows us to have additional knowledge extracted beyond the explicitly stated information. What does that mean? Using simple words. We can exploit class hierarchies and properties through the inverse properties in order to have additional information reused and have some information extracted from the existing one. Can you please remove my... Yes, the camera. Yeah, because I want to show something from this image. So, if you could see there, we have the sculpture, an image of the sculpture of Laocoon, and a 3D model right next to it. Let's imagine that we have used this 3D model in many different events, like simulation events or transformation operations that have taken place with this 3D model as an input. When we apply inference, it means that we can query our system towards that actually connect the lower events like simulation, transformation of operations and formal derivations with a specific object we are interested in. So we can exploit these hierarchies and query super classes, let's call them, in order to get results even from subclasses without explicitly stating these subclasses in the query that we use. This is also a fact. This happens also when we exploit the inverse properties, like the L10 had input. So imagine that we have a digital machine event that has as input a 3D model. We can also use the inverse property L10I was input of in order to efficiently navigate throughout this graph structure and get more results, more information coming back while traversing the paths and the edges of our structural graph. So, everything connected. All the information we have is being expressed using RHDTO and is then imported into semantic graph database system, specifically GraphDB. We use GraphDB in the ARTEMIS data infrastructure, where the semantic relationships explicitly connect our assets, the data, and the processes. Users can navigate through the visual graph, or if they're experienced users, can also use a specific query language that we use for RDF data, which is SparkQL. The aggregation pipeline that we plan to follow, some steps are still under development, and this is why I mentioned it as a plan to follow. We will start by collecting the information, the data, from different sources, mapping them into our ontology and transforming them in a form that is compatible with our system, which is RDF. Then this will be ingested into GraphDB, enriched using existing vocabularies, existing ontologies and vocabularies, and the outcome will then be publicly available for people to access and query. This is a pipeline that has been designed according to the experience my collaborators here have from the Ariadne research infrastructure, but there are some new characteristics that have been defined, have been added to the pipeline, where you can see AI and LLMs being exploited in the case of the mapping and the access and query steps. But my collaborators will tell you more things about it in a while. So, from semantic to smart access, RHDTO and the knowledge base together provide the stable semantic foundation of Artemis, and on top of that, we are able to build additional knowledge, to build intelligent systems, and to have smart outcomes. What we want from an RHDT and from our system, in general, the data infrastructure, is not only to describe the assets, but also understand their history, their behavior, and their vulnerabilities. So, having defined a coherent structure for our data, we are now able to build on top of them smart methods and smart techniques. I will now leave the floor for this to Mirjana. Thank you.
Okay. Can you hear me? I don't know. Yes? Okay. Yes? Okay. Hello, everybody. I'm Mirjana, and thank you, Vicky, for the wonderful presentation before mine. Can you see? Okay, yes. So as Vicky mentioned, I'm going to give you a briefly introduction about how we chose to use some AI models, namely large language models, to populate the ARTEMIS knowledge base. Before that, we need to take a step back. So about the cultural heritage data state right now. So cultural heritage data today is vast, diverse, and is often unstructured, and that is the problem for machines. It includes text, reports, papers, scientific analysis, tables, images, a lot of different things. So we are facing an information chaos, a lot of things, a lot of relevant things, but also a lot of irrelevant things. And we need to travel our ways through this chaos. We chose to start with the most relevant source, of cultural heritage data right now, which is textual information. We started by collecting raw text from PDFs, reports, scientific analysis, and all sort of similar things. But once we have the raw text, a problem arises, which is text is unstructured as it is. So we need a way to transform it into structured knowledge. To provide an efficient backbone for the heritage digital twins, which are knowledge graph, as Vicky already mentioned. Knowledge graph because they are backed up by ontologies, which allows the semantic layer to be there. They preserve the context, the relationship between the entities, and the meaning, which is crucial, especially for cultural heritage. And they also enable features like multilingual representation and provenance tracking, which is also very important. So what is the issue then? The issue is that creating knowledge graphs from documents is a slow and manual process. Imagine you have PDFs, hundreds of them, thousands of them. A single PDFs about one scientific analysis on one singular micro things can be up to 20 pages. So you need to read the full text and understand which are the relevant information to then map them into the ontologies. So to do that, you need to know ontologies, and you need to know which are the relevant information. And there lies the issue we are facing. So most domain experts have a lot of data, they have the data, but they don't have the knowledge or expertise in the semantic and ontology part. So they cannot annotate their data properly to serve as the backbone for our knowledge base. So we thought, what if there was an AI-based assistant that could help us read the scientific documents and extract structured knowledge directly? So what we decided to do was to try and use an open source LLMs, because everything we're using is open source in compliance to the European Union laws. And we decided to try and elaborate an AI-powered assistant for semantic annotation. So to help people go from the raw text inside the documents to the actual ontological mapping, the right ones. I'm not going into the too boring and technical part here, but we extract the term, we use the LLMs to do it, we group them semantically, we store them semantically in an embedding database. Embeddings is the way of represent meaning numerically. And then we validate them having humans in the loop, because also human expertise, especially in cultural heritage field, is very important. And then we extract from that the RDF triples to then populate the knowledge base. So we go basically from the scientific PDF about, in this case, it was a coin found in a place with a material and whatever, to the actual graph and annotated in a correct way. Of course, we use both our ontology that my colleagues are developing and also the existing ones. Why this approach could be a game changer? Because it's very, very fast compared to manually doing it every time. And it's also accessible because it makes the data more accessible for also curators and researchers that has curational expertise but not computer scientist expertise. It's adaptable because even if a new ontology comes up, we can also train the same LLM with the new ontology. It's reusable because we can use it in different domains, and it also collaborative because it also takes into account the human expert validation, which is essential for accuracy. Of course, it's not just about words. We also have a lot of images and scans and pictures inside the cultural heritage data. So we are also working towards using vision language models, so a step further than just language models, to help automatically identify, classify, and map and tag these images in the correct way, to then enrich our knowledge base even more and have the biggest base possible of data. AI, of course, can be used for a lot of things, and I will leave this as a note for my colleague Aida to follow the speech. Thank you.
Well, first of all, Thank you, Miriana, for such a smooth transition into the topic. Now that we've built these knowledge graphs, now that we've structured them, we have populated them, how can we query them? How can we interact with them and retrieve information from them? Because that's how we use the data that we've worked so hard to get. We propose as well an AI-powered solution for this, simply because there are a few problems with traditional knowledge graph querying. Knowledge graphs for cultural heritage data is often and should be large scale for the amount of data that's out there to structure, and complex for the ontologies according to which they are structured. They also require expertise with rigid graph querying languages, namely SparkQL, which needs its users to know exactly the syntax, the entities that they need to look for, the properties, etc. And any mistake in such a query can and will lead it to failure. And not only are they complex syntax-wise, and they can be very long when you are looking for something very specific in such a large amount of data, they can also be very expensive to execute because of the large amount of data that they need to search through. So we need a smarter approach. The approach is using an AI models to streamline this kind of process. And so AI models need numbers. Let's give them numbers. The idea is to give the subgraphs, the knowledge graph subgraphs, and also the queries numerical representations, namely embeddings, as Miriana has said. These act like fingerprints for the meaning of these elements. So for an example, we have a node Leonardo da Vinci. It has its numerical representation, which is its own fingerprint. The edge created has its own fingerprint. A relationship can have this embedding fingerprint, and then a subgraph can have this fingerprint. So we see that the semantic data, semantic information is encoded and preserved through different levels of the knowledge graph. And then we compare these for closest relevant results instead of aiming for exact matches as we would have with SparkQL. Why does this work? Simply because nodes and elements of a graph with similar meaning end up with a similar numerical representation in the numerical space, similar fingerprints, if you may, and so similar meaning, similar numbers, easier and smarter search. How did we use this approach that we were suggesting? We have used it first in a natural language querying feature. So the input would be a natural language query, find artworks by artists who studied in Florence in the 16th century. This is a very vague query, but it can be a case for someone who just wants to look for these artworks. What happens to it is we parse it using NLP techniques, LLMs, for the natural language understanding part to identify key elements, so exactly what Miriana has explained. After that, we transform it itself into a query, so into a query graph. So whatever the user asked is becoming a graph itself. So again, the same thing that's happening on the knowledge graph to structure it is happening on the query. We want to make them as comparable as possible. A fingerprint is given to this query graph with its elements, and then the only thing that's left is compare the similarity in that numerical space. The things that are dissimilar are close, so we have a smaller scope to search through. The similarity computation can give us results on many fronts. For example, pieces that belong to the same object, different objects that were excavated at the same site but from different locations, different objects that were crafted in the same workshop, different objects made of material originating from the same place, which is data that can be inferred from the scientific analysis reports in the knowledge graph, and different objects made by the same artist, which are all things that a person who is searching for data wants to find, and they're not explicitly stated in the data as it's being structured. To conclude this long presentation, we would like to talk about the future works that we have already an implementation schema for, and we'll start working on as soon as the data is readily available. First one is foresight. So in addition to querying and interacting with the graph, we want to use this data alongside other data, integrating learned historical scientific data from the knowledge base and data collected from sensors, so real-time data or data that is aggregated periodically, feed them through an AI prediction module, and have that module predict us potential danger or damage that would occur on an artifact, on a physical, maybe on a location, on something, depending on that data that it is collecting and the data that it knows. So it would give us early warning systems for physical decay, data-driven conservation planning, and it would aid to enrich digital twins as predictive tools instead of just information holders. The other one is simulation. This one is slightly different from the last because we're not giving it real data from sensors, we're giving it hypothetical data. What if these were the parameters right now? What does that change? How does that affect the artifact? So we give it this and the learned knowledge graph data through an AI simulation module that gives us exactly the scenario-driven support for preservation and policy. This is very important for people who are working on the artifacts and need to restore it or need to use certain techniques. It would be better to simulate before actually touching the physical artifact because that's a very expensive mistake if such needs to happen. And so it sets the ground for AI as a partner in heritage futures planning. Only thing that's left is for the ones who are not partners in this project to become a partner and trust us with their data. And it is certainly going to be put in good use. So thank you for listening, and thank you to my colleagues for such an amazing presentation.
Thank you, ladies. Beautiful presentation. I wonder if we may have questions from the audience to this first presentation. Questions from the audience? Yes, please. Claudia.
Actually, first of all, beautiful presentations. I've been at hundreds of cultural heritage conferences. It's really good. Thank you. Yeah, the question is, all this implies a kind of implicit feeling that we have everything in our own database. But the reality of the world that every museum uses different systems, etc. So there are a lot of this database. So actually, the question is, it works inside because you implicitly assume that you have identifiers of your database. So the same object, which has the same identifier, in other museum, in other system has different identifier. Have you thought what are you going to do with this hell of identifiers when you go to the real world? Because that's quite a big challenging question.
To answer, please, you can go there.
Please, Vicky.
This is a case with all repositories or all systems that collect huge amounts of data. No, yeah, I understand. But this is actually addressed using the unique identifiers, permanent identifiers, the main identifier of the system, and many alternatives that can be also populated within our knowledge base. So first of all, we don't need to have the data inside our system. We can only store the metadata, and the data can rely to other systems outside our system. And using the main identifier of the object, we can interlink through linked open data principles all the other identifiers in other systems. If I don't understand, I don't know whether I haven't understood your question properly, but I don't, yeah.
Inside the system, you have a registry of all these identifiers.
Yeah.
Your system, probably your specific system will live, let's say, 20 years, okay, 100 years.
100 years, yeah.
But of course, we expect more.
Mm-hmm.
Point is that when your system dies, together with the registry, not this data, this one, registry will die.
Mm-hmm.
The moment the registry is dead, nobody will find anything this mess. So if you're talking about long-term preservation of data for hundreds of years, you need to make sure identifiers survive hundreds of years.
Of course.
Your identifiers will survive as long as the system, but practically it might survive 3 years, 5 years in reality. So real problem is that the time span of every specific system
Mm-hmm.
then goes the end of the registry, end of identifier. So all the beautiful work may disappear simply because there is complexity.
This is in general the problem of identifiers, and yeah, I mean, it's not a problem of ARTEMIS, but we keep alternative identifiers within our systems in order to link all these different sources and have the most, rich collection of identifiers if they are different throughout the ecosystem of the cultural heritage. Of course, we will use our own identifiers to get them identified within our system, but the permanent identifiers of all assets need to be directly addressed and collected within our system.
Thank you, Vicky. I had this problem times and again. I wonder we should have Daria members here to continue the discussion. We discussed it this time about long-term preservation. We have, as data producers, I was the coordinator of a data producing infrastructure. And when we produce data, we measure something, we have the problem of describing the measure, including the object. It would be very nice if we can point to a unique identifier of the cultural objects we measured, but we have still to compile data about the object because nobody is providing unique identifier of cultural heritage objects around yet. Anyway, if you want to preserve something for 400 years, considering the current technologies, print with good ink.
This question came, the whole idea link data was invented by Kim Berners, and then he invented the solid project. And actually my team, we have a long discussion with his team about this identifier, so I know that wherever we use link data, we get these identifiers, and it's a very ancient and big problem. Link data is beautiful, but we need to put foundation of identifiers.
Yeah, a provider online of unique identifiers of heritage objects will be excellent. So when I do anything on an object, I point to the DOI of the object, somewhere stored and long-term preserved and unique. But this is not anywhere currently. It's a problem yet to be solved by everybody, not just by Artemis. Well, okay, if I would be, I vote for me and I will promote. Okay, thank you again, lady. I suspect that the second presentation in the list is concerning services. Wow, 109 services.
This is
Soon to be.
the same of Monday. But
Develop someone on Monday
in these hours, yes, because Franco told me yesterday to be more visual. So, in order to say something about the identifier issue, I think that in the near future, generative AI, both for textual comprehension, but also coupled with the visual comprehension, could help to solve this problem. I think that the good risk in the near future is that identifier is not needed more. Has not been needed more, in my opinion. Yeah. We don't. Yeah, sure. So I have a subset of slides expected to that one. Don't worry, and I will be a little bit more visual, okay? So the topics that I will cover are the same, and I want just to start to say that starting from what Franco presented this morning, we understand one important thing. That is that Artemis infrastructure or Artemis technology is not the big software that solves every problem that we can have in the cultural heritage domain. So when we start to work with the service of the infrastructure, we think, starting from the beginning, that the nervous system, I want to use the same metaphor of Franco, has to be made by not one software, but by many little pieces of software that run somewhere, in our case, partially or almost partially in the back end of our infrastructure. And these specialized software do less functionality, but work together in order to solve some specific issue. So, for understanding this thing, I want to be much visual, okay? So, let's go to see, for instance, this is one of our pilot. This is the pilot. We are working on this pilot. This is one of the more than 20 pilots that we have and anesthesia, I think that we show later. And this is a screen case, and the screen inside there is a book, an ancient book, and we can imagine that this book need to stay in a perfect ambient condition. So the light has to be at the right intensity. Maybe the roof, sure. So you know now the design is really this one. So you can imagine that inside there are many sensors. For instance, there is a light sensors, is a humidity sensors, a temperature sensors, but we have also many actuators. One actuators work as dimming the light or rise the temperature. There is a Peltier cell for tuning, for the tuning of the humidity, and also the glass rise from the floor in order to protect the book, everything that is put it inside. Okay, so let we see how the screen case work. We turn on, we powered the screen case. So there are some software that run within the microcontroller that stay inside, and the microcontroller do less, is not a big edge computing. For instance, the sensors that measure temperature do some things like that. Each second, take 10 measures, waste the height one, the lower one, and average the next measure. So it's a simple way to use an IoT node. So each second, this node send to the, I need to stop, send this information each minute to the ARTEMIS framework, where are catched from the services that run within the ARTEMIS. So there are a specialized service that have this function. Please, sensor, give me your data. What this service do with the data? Store this information in the container that, for instance, we already seen before. Okay. Let's continue to understand these things. This data come in the knowledge base if is a structural data. For instance, I'm a sensor number 5. I'm here in the Louvre, for instance. Or my measure is 5, and these are operational data, stay in the structure in the back end, and are stored inside this container. Well, let's try to continue the simulation. This data, the sensor, now at this point, the service has to take a decision. The decision, for taking the decision, the service that takes the decision has to read the data that are stored, the story of the data stored in the knowledge base and in the operational database. Well, the decision is taken. These services cooperate in order to take the decision and, for instance, open the glass or dimmer the light or do something. Well, but imagine this thing. If I dimmer the light, I give a value much higher, the temperature rises at the same time. If I open the glass, the humidity level that stay in the room come inside, so acting, this means that acting for tuning one parameter can be in contrast with the other parameters. So in our services, you will find, surely, there are some services that take this decision. If you stay over a threshold, do something. If you stay under a decision, close or open. But there are also more complex decisions to take. And this decision could be automatic. For instance, an idea where a group, a team is working is to use mathematical programming with integrating inside machine learning in order to optimize and predict what will happen in the near future, okay? And we need to have, if we want to apply a decision like that, we need to have a specific service that has to be general and has to do this work for us. Question, this is a digital twin. It takes data from the real world. This data come in the back end. The back end take a decision. Is a basic reality. Is something like domotic. This is the first level of digital twin. But there is no human in this loop. We need to add a human. Well, in our mind, to add a human, we enrich the number of services. We add some services that give the opportunity to a human to push the button if it's needed. So continuing our loop, also the application can fire this service, and this service take data, interact with, stop here, interact with the knowledge base and the operational data, and give the possibility to have updated a graphic like this to the human operator. This is a digital twin. Yes, it's a little bit more complex, but it's a basic digital twin again. In our mind, the reactive digital twin managed by our project, in our mind, has to be to do something more. That is the key. What happens if not only data come here in the human interface, in the application? What happens if also functionality come in this direction? We can imagine something that is a human interface or an application, and the idea is to take all these services and see the services as services that give data and knowledge, and services that give functionality to the application. The functionality must to be mixed like a Lego brick in order to do a more interactive digital twin. For instance, give the opportunity to have not only a 3D visualization, but more than a 3D visualization. Is a real digital replica of what happened in the real world. And the flow of data, the triggered events come from the real world to the digital replica, but also can rise on the digital replica and have some effect in the real world. So, if we in this case, we can see the application as a cocktail of services. And we can have a more rich interaction level that could be this one, dedicated. This will be of, but could be also a cooperative level in of the human in this loop. Well, how many services we need for doing this? Okay, and we have our result of the first year. So you have to look the beautiful, so this is all the driver that we follow for for define the granularity of the services that we need, and we have to be, the most important thing is this one, reusability. This means that a services will be a services of Artemis if this service is useful for many applications, so it's common to many applications. Well, I go directly to the services. So we need three legs. The first leg is the IoT technology. The second leg is simulation. The first leg is the interaction. So we have three groups of services. In IoT category, we define 32 services that cover all these topic. In the simulation, for the simulation, we have 41 services that cover all the these subgroup of these needs. And finally, we have 41 services, of course, because digital twin need to interact in that way, in that level, with that level, with the 3D and immersive and cooperative interaction. We have 41 services at the moment designed for the Artemis framework. The total, you already know the number. We know the number too, because we started in the last month to develop the first group. At the moment, we are working on this 32, and our partners are working in these 41 services. And there is the possibility also to attach to the group also external services and other services that are useful for querying the knowledge base that we already see. So it is necessary for a digital twin to integrate all the 109 services. No, it depends. Artemis must to expose all the 100. So we will work in order to have all the more than 100 services that run on the framework, on the back end. But it is possible to decide what level of conformancy you can have in integrate the services of the framework. You can start with the foundational part. So I want to integrate just the baseline, the semantic interoperability. So this meaning that my application share knowledge and take knowledge from the backend, from the knowledge base. If I integrate one of these three group of services, I can stay in conformance class 1, more than one in conformance class 2. The display case that we see before is in conformance class 3 because we'll integrate the three group of services. So this gives us the possibility to rise the functionality of an application and gradually entry within this ecosystem, digital ecosystem, I say. Okay. Thank you so much from all the WP9 team. Okay.
Thank you very much, Lucio. I have to quote a very famous book to the benefit of Achille. Once the answer to the question about life and universe and everything was 42. In the case of Artemis, it looks like it's 109. Any questions from the audience?
I know that my stakeholders are developers of applications, so if there is some question.
Please.
I'm here.
Sorry, it's me again.
You're welcome.
You're welcome.
It might be much more than 100, we're talking about probably millions. Point is that this stands in the building. There is condition system.
Yeah.
There is system which controls the windows.
Yeah.
So we get to smart home stuff.
Yeah.
So actually you get to situation when you have amount of actuators or sensors.
Yeah.
Cannot hear online, it seems.
They should.
Closer, maybe.
Okay, they're here now. So actually we have big amount of actuators, sensors, but also applications. Also insurance company also want to have a look at it. Bank wants to have a look at it. Fire service want to have a look at it, etc., etc. But also the pressure of the water provided by the station, the city also affected. So point is, it's quite endless process. Question is it for Artemis to get to smart home stuff, etc.? Probably it's difficult. But actually, we may need to start talking. Is the next stage. What you demonstrate is really great. But as the next stage, we might need about talking of data space, which connects together smart homes, city management, museum management, financial management. So it was a great example when things get out of control, go to other domains. So it was just a comment. We have, I mean, my team, we have an idea what we're talking about. So, but actually, you opened a door to the great world outside of the museum, so it cannot be done by just Artemis, but it's great that you open the door, and I like it that you, so we have to explore it further, much further.
Yeah, you cover.
We call data
an
space.
Important topic, in my opinion, because this touch precisely the each process that has to take a decision. So it is important. So. If you have, for instance, what you said before, a combinatorial problem that is more complex, there are some approach to solve some specific problem, but typically this approach need the dataset, and so what you say is important because this is the basic needs that we have to integrate not only the knowledge base but also the operational data are very important. But the most big is the container of information that could be linked, of course. The most precise will be the decision. So you touch the problem. Yes, sure.
There's another question there from our friend Alessandro.
So I have a question, but it is not a question, it is a comment. And I'm looking after Artemis, okay? And the point is, what happened? So who is the responsible of the application services, whatever, of the 109 services that we, in some way, we develop? I mean, speaking about, for example, security, who is taking care of the update or the library, whatever? No.
Simple answer.
No.
Yes, now
Yeah, but
following
the answer
following
is
the
simple, but
serious
it's
answer,
wrong.
of course.
The answer is simple, but it's wrong.
You have to live in the future. Typical, sure. This is a research project, a big research project that coexists with other big research projects. And after the end of the project, we have to demonstrate that something is possible and feasible. Of course, if we want to go in the market, we have to invest more in the future and solve not only this problem. There is another set of problems to solve in this case. In this period, I have for another, you know, that's as a researcher. I work for many years in the IoT field, and Smart Education Lab is a partner of this consortium that I represent here. Is in this situation, after 4 years ago, a research process has finished, so money has finished, we decide to go in the market with the result. And we have to find many funding, private funding, for arrive to have the TRL 9, that is the minimum to stay in the market. So I know what I'm talking about in this case.
That is exactly the problem that we will follow Artemis. Andrea, please.
Andrea.
Quick observation, I really loved your comment about smart home application providers. Some of them are going into museums with enough money for them to pay them to customize the smart home system. So extremely complex systems that do this already exist. So for me, the critical point is, how are they going to interface with Artemis? And I see they're either going to be interfacing with Artemis, or they're going to be working against Artemis as competitors. And I see 2 ways this could unfold. It could unfold top-down.
Yeah.
The director of the museum forces them to interface with Artemis because it has the data knowledge, because we have to keep track of the objects and enhance the metadata. So they will be forced to work with us. Or bottom-up, Artemis gives them a clear value proposition.
Sure.
And that needs to be, still needs to be formulated. I think it's there. It's in the beauty of the work
You-
and the
you have
idea,
to
but we
imagine
have
that,
to still verbalize it. We
The
haven't
number
verbalized
and the
it.
quality of services, we are now focused 100 services, but this number could rise over time. So if something new born, and there could be a service that could solve some problem. Now we are driven from the pilot. This means that the priority in terms of developing this huge amount of service has to come from a pilot. For instance, we start to develop all the services for managing IoT nodes because many pilots need this functionality. But the timing is flexible, starting by now till the end of the project. So, you know, for instance, if you look this one, if you look this visualization, here you don't have only the information, how is in this moment the temperature. You have another information, it's much more complex, how this temperature is distributed within this screen case. It's not the same. It's not the same. So we start to develop the service that give you the information homogeneous way, but we need, in order to reach this objective, we need to add some more complex service that give you the opportunity to distribute in a shape, in a volume, the distribution of temperature. So it's important to start to have a strong basic number of services and try to raise the complexity.
Another question from Andrea? Or a comment?
I would like to comment to a very good question. Actually, we all get to a kind of trap here, because it's always like a pair of sensor actuators here, some kind of controller, and then some information system, ARTEMIS. The guys who provide home security, whatever, they also have some, controller which controls condition, and then system which controls it all. So you're talking about connecting their system to Artemis. It looks simple, API, but reality is much more crazy, because amount of systems in the world, millions, amount of Artemis-like applications, millions. So we're talking about connecting end to end. When you have n connections, actually we're talking about n square connections. European Commission tried to address this issue through European data space. Let's connect all the systems through these n square connections, but they failed because n square is a very big number. It doesn't work at all. After 3 billion euros spent on this way, European Commission now, I don't know what they're going to do, but separate discussion. The only answer which could be that every controller, like this stand, should communicate not only with its own parent system, but with anyone. That's the answer. So Artemis can access any controller of any device, but at the same time, home application can access any controller, including your booth, or insurance company can access. So the only answer, when you separate data from platforms, then you have data separately at every controller, and then any system can access it. Then you have n connections. So this is n square riddle we get here. But you see it only when you zoom out and you see from the big distance.
Sir, I have to ask something really quickly. So for me, my answer to that is it has to happen bottom up. Like, we are in fantasy land when we try to say, okay, n to the n to the n to the n. Of course, the space is millions, but the reality has to come from the ground. It has to come from demand. It has to come from actual museums coming to us with actual problems. And the more we solve the problems they have, the more we provide solutions, the more this space, of course, will grow in complexity. But it will not grow as a fantasy n to the n. It will grow from the bottom up, driven by real demand and the real world.
This pilot was guided by a museum. Another thing they ask to explore, and we try to do this, if to use the actuators of the glass for prevent the vandalism attack. There is some research, the basic research already done, and we can try to, not to solve, but to try to give an answer to this problem.
Are you able to identify people with tomato sauce
No,
in their bags?
identify dynamic, because we don't,
No.
with the GPRM,
Yep.
you don't have the opportunity to understand the face of someone, but it's possible to track the dynamic of what happened in terms of just dynamic near around the screen case, and try with, for instance, a machine learning approach to predict some dynamic disaster manner.
I suggest you give your card to the Louvre. They may be interested.
For work.
So, sorry. We have to go on.
Sure.
We have to go on. Let's keep our feet on the ground. We are just to demonstrate the concept of reactive heritage digital twin. We end with TRL 6, so then to go to TRL 9, it will be blood and tears for some years maybe. And the fact stays that we are even trying to demonstrate a technology that, to be fully exploited, should benefit of integrated data on cultural heritage, which are not very common in these years. Because, as we were discussing, if you have to build your digital reactive twin and you lack the data on the object, you have start with the data capturing campaign, which is terribly expensive. And so your model is not going to be used because nobody is going to pay 1 million for data acquisition campaign in order for you to use the digital twin. So we hope that the ecosystem will go in the direction of other people solving the problem of lack of data about heritage. Otherwise, ours is a beautiful demonstration of digital power, but we stay there.
Okay, thank you.
Okay,
Thank you so much.
thank you everybody. Now, this is Napolitan. Now, Anestis from
from
From the remote world?
The remote world.
Okay, okay.
Has sent us a recording.
So please evoke Anestis from the remote world. And
A recording of a recording of a presentation of the piloting activities.
Anestis digital twin will introduce the pilots.
Hello everyone, my name is Anestis Koutsoudis. I'm a research director at the Athena Research and Innovation Center in Greece, and I will be giving a short presentation of an overview and the main objectives of the pilot cases designed within the ARTEMIS project. Let's start with how we define the term pilot in ARTEMIS project. A pilot is a real-world experiment designed to validate one or more ARTEMIS technologies against specific cultural heritage-related scenarios. A pilot revolves around one or more cultural heritage assets of any scale and defines concise objectives relevant to cultural heritage professionals together with measurable success criteria. In fact, a pilot aims to produce evidence and feedback that support the assessment of ARTEMIS technologies in practice. Pilots in ARTEMIS aim on creating RHDTs. But what are they? RHDTs are reactive heritage digital twins. They are a dynamic, semantically rich digital representation of a cultural heritage asset that continuously integrates data derived from sensors, documentation sources, and expert annotations and documentation. It is reactive in a sense that is able to update in real time, allowing changes in condition, environment, or usage to immediately influence the state of the digital model. Furthermore, by combining monitoring, simulation, and decision support tools, an RHDT enables cultural heritage professionals as well as cultural heritage stakeholders to understand a cultural heritage asset evolution over time, assess its risks, and plan suitable interventions. It should be noted that an RHDT is not just an annotated 3D digital replica. It is not just an annotated 3D model. Actually, the 3D model provides a spatial anchor for the data in analysis within the RHDT while enabling sophisticated visualization either through a desktop device, a mobile device, or an extended reality headset. Each one of the proposed ARTEMIS pilot cases is supported by a range of complementary technologies that work together to deliver the RHDT concept in practice. In this slide, you can see some of these key technologies used in the ARTEMIS project organized into three main groups. The first group is the one that is focused on functional and user-facing technologies, and it's actually defined what pilots do, what are the core technologies behind them. This is the teal color. The next group, depicted in the yellow boxes, is focused on the integration and infrastructure technologies. It indicates how pilots connect. The last one, which is the semantic backbone, those technologies depicted in the light green boxes are the semantic and knowledge infrastructure that indicate how pilots understand and relate. In each one of these categories, you may find well-known technologies that all of them together are utilized within pilot ideas through different approximations or through the same ARTEMIS services in order to enable each one of the pilot cases, each one of the pilot ideas to demonstrate specific tasks relevant to cultural heritage professionals and stakeholders. Currently, we have designed 14 pilot cases, and a few more will be completed by January 2026. We have grouped those pilot cases based on their core objectives. The four groups in this slide is the result of this grouping. The first group of pilots is focused on monitoring, diagnostics, and preventive conservation, and it holds pilots whose core aim is to monitor the environmental, structural, or physical conditions of cultural heritage assets to support risk mitigation and early intervention. The second group, the digital reconstruction, interpretation, and knowledge sharing and/or enrichment, is composed by pilots dedicated to reconstructing past states, interpreting historical context, or semantically enriching cultural heritage knowledge. The third group, the urban, architectural, and landscape scale heritage modeling, is composed by pilots whose core aim is to model, simulate, or manage cultural heritage at building block, settlement, or landscape scales. The last group, the large-scale, multi-site, and national level risk assessment, is a category where we have currently only one pilot. That pilot has a main objective to analyze risks, integrate large data sets, or support cross-border and national cultural heritage authorities. In most of the cases, we have pilots that fall into more than one group. We designed the pilots in a way that they are mapped to real-world risks. In that way, we ensured that they are relevant, actionable, and grounded in the realities faced by cultural heritage today. As you can see from the slide, there are 7 different risk categories that our proposed pilots can be mapped. Those categories are the climate and microclimate-driven deterioration, structural decay and loss of integrity, fragmentation and loss of context, overvisitation and crowd pressures, landscape-scale environmental risks, and national-scale threats such as floods, storms, climate events, and conservation, decision-making under uncertainty. ARTEMIS pilots address different types of cultural heritage asset domains, different types of assets if you prefer. In this slide, we depict the asset domains addressed by the pilots. The numbers in each grey box indicate the number of pilots relevant to that specific asset domain. It is obvious from the slide that the pilots cover a broad spectrum of cultural heritage asset types, starting from movable heritage, such as painting and sculptures, moving to single buildings and monumental structures where we can find palaces and historic houses or even windmills, moving to historic urban assemblies and city centers, historic city centers, moving on to architectural elements and historic interiors such as frescoed rooms, decorative seams and historic furnishings, moving to archaeological sites and excavated heritage where we find mosaic, burial monuments, open-air archaeological contexts, then the cultural landscapes and forest heritage where we find monastic landscapes, forest heritage sites, villages embedded in natural settings. Last but not least, the national scale distributed heritage networks where large institutional collections, multi-site heritage infrastructures, and country-wide inventories. But what are the actual cultural heritage assets addressed by our pilots? In these slides, we are trying to be a bit more specific. In the first group, in the movable heritage and museum collections, we have the presentation of the temple by Francesco Curadi. We have the Penitent Magdalene, a sculpture by Desiderio de Sataniano. We have artifacts from the Gruthus Museum in Belgium. We have fragments from the Nidaros Cathedral in Norway. And we have Cossack crosses and grave slabs from the Kualnik Cemetery in Ukraine. On the second group, in the architectural elements and historic interiors, some of our pilots are focused on the Saturn room of the Palazzo Pitti in Italy, Giovanni Pisano's pulpit in the Church of Sant'Andrea in Pistoia, and the apartments of Napoleon III on Louvre Palace in France. In terms of single buildings and monumental structures, we have the Belheim Palace in the UK, the Grand Maison in Greece, which is the house where Manos Hatzidakis, the famous Greek composer and musician, was born, and in Belgium we have the Flemish windmills. Moving on, in the archaeological and cultural heritage sites, we have the Pygmeos mosaic, an Italic archaeological site in Spain, a national network of almost 9,000 archaeological and heritage sites from Slovenia. In the group of historic urban areas, we have the old town of Xanthi. And in the group of cultural landscapes and rural settlements, we have the Vallombrosa Silvo Museum and Forest Heritage Landscape and the Caldana Renaissance Village. Let me now highlight what are the cultural heritage stakeholders and professionals involved in ARTEMIS pilots. In fact, our pilots demonstrate a diverse spectrum of stakeholders and professionals' involvement at various implementation stages, starting from the design, the implementation, the evaluation, and of course the future use of the tools that are going to be developed by each one of the pilots and generally the ARTEMIS infrastructure. In the orange boxes, you can see those professions organized from the most popular to the least popular as they've been addressed by the various pilots of ARTEMIS. The most popular group is the conservator and restorers. It should be noted that the numbers you see in the gray boxes under each one of these groups is actually the IDs of the pilots that are focused or involved in some way those cultural heritage professionals. After the conservators and restorers, we are moving to the curators and museum collection managers, the heritage site and building managers, the heritage authorities and governmental agencies, moving on to municipalities and local administration, structural and building engineers, archaeologists, and the researchers and academics coming from multiple disciplines are highly represented across the entire pilot set. So I will conclude my presentation by giving you a sneak preview of a tool we are currently working on within the ARTEMIS project. It's the VAX annotator. The video demonstrates two people using this environment. It's a dedicated virtual environment designed for use with XR headsets and thus enables an immersive interaction with digital representations of cultural heritage assets. The tool aims to support collaborative analysis and interaction, as you can see, composing a versatile platform that will be utilized by several pilots within the ARTEMIS project. It enables users to perform multimodal annotations such as point-based, surface-based, volume-based annotations, or you can even annotate a 3D model by using images, such as this example you are currently seeing, where the user has an architectural design of the balcony, and he places it in the correct position in order to enhance the visualization of the 3D model with architectural informations. It enables the monitoring of data streams for IoT sensors and many other different types of on-demand annotations. In this example now, we have the old town of Xanthi, where the annotator is going to be utilized to start designing the scenarios of various crowd simulation tests that are relevant with, let's say, annual events that take place in the historic center of Xanthi, and authorities need to quantify and address specific situations relevant with either large number of people walking in the city center, or in bad situations where they need to evacuate the historic center. The VAX annotator will also be a visualization tool for the results produced by a crowd simulator in order for people to collaboratively assess the simulation outcomes in almost real time. And this concludes my presentation. Thank you for your attention.
Thank you, Anestis, if you are online.
Question for Anestis?
By phone? Do we have the phone number of Anestis to ask questions? Okay, with this presentation, I think we conclude the technical nodes of the project. And so we are now going to training, capacity building, and finally we will conclude with outreach and dissemination to give the complete overview of the project activities. Elizabeth, our package leader of training, please.
Mouse or keyboard?
Don't worry, I will start. Put it on the screen.
Okay, thank you.
In 40 seconds.
Okay. So good afternoon, everybody, and great to see you all here. Many of you know me by now. My name is Elizabeth, and I'm here to represent the training work package in ARTEMIS. And I would like to start with this quote from our website, basically, that was created to kind of sum up what training is supposed to be and to do in ARTEMIS. It is supposed to be, as it says here, a training that grows with you, and you means the community. The community is not only the people who are in the project, who are experts, and you have heard a lot from these experts in the last few minutes. It is also the people who are supposed to use ARTEMIS and its tools and its services within their actual work environment, meaning a museum, an archive, a research center, etc. So what we need to do is not only, as it has been already discussed, a top-down approach where we present our innovations and expect people to use it, but we also want to have a bottom-up approach, looking into the community, asking the community what we can do for them. And ARTEMIS is there to provide solutions, potential solutions to challenges that we currently face in preserving cultural heritage, in managing risks, in working with our digital twins and enhancing them to become reactive and thus help us to preserve what we currently have for the future. We do this in ARTEMIS training to create and to work with this community in two ways. For one, we envision to have various on-site, in-person events, but we also utilize modern-day environments, digital environments, by having a dedicated training platform. Better said, utilizing an already existing training platform, because it's already been addressed. Reusability, consistency, and persistence is key to retain an audience and to retain the training. So first of all, I'd like to introduce you to the platform that we are using for the training to keep our training alive for the time of the project and forward. This platform is called Daria Campus, and Daria Campus is a so-called discovery framework and hosting platform for so-called open educational resources. That's very important because it means we go outside the silo. We want it to be open and accessible for everyone, irrespective of which institution you belong to, your financial backgrounds, your educational backgrounds. Anybody is allowed to use it to their own means. Daria Campus is a core service of the Daria ERIC, and it was launched already in 2019, and ever since has undergone changes and innovations to make it ready for the present day challenges. And it offers this free open access resources, particularly in the digital arts and humanities, but also expanding further and beyond that, for example, with ARTEMIS, where we also look into archaeology. And it allows for multiple formats, and I will show you this in a minute. We have different formats per se on the platform, starting with the most nuclear version of training, which is a so-called course. So it's a singular training event on a specific topic. Can vary in size, can vary in difficulty, but it's one unit, so to say, that you can use. And these courses can be compiled into so-called curricula, which will be one of the outcomes of the ARTEMIS project, to have a dedicated curriculum for ARTEMIS that tries to encompass many topics that are addressed in the project. And the benefit is that you have sequential learning, so starting from rather general, simple matters to getting into more complexity. It's coherent, there's progression, and it's aligned to assessment. And we also have a resource that is called the Pathfinder, and you can imagine it like an annotated reading list. So it's a resource that does not necessarily comprise newly created resources of learning and training, but it shows you what is already out there and what can you use to upskill in whatever area you need it. I'm not going to show you this video, but it's lovely. So the important part is it's on the one hand great for learners because it's open resource. It's an open educational resource. On the other hand, it supports those who create the training, and that's the other side of the coin, because you also need to support the ones who want to train people. It's versionable. We have in the background a Git, what is it? We have Git running in the background. That means basically it's a repo. You can download that repo to your computer. It's very lightfoot, so it's easy to download. You know, you can use it pretty much everywhere if you wanted to, or you'd simply go online on the website and use it there. And what has already been addressed in this meeting is for the training resource, it creates so-called persistent identifiers and automated citations. So you generate metadata with it, and you can use it further beyond project existence, for example. And of course, this has the issue of what is long-term preservation in digital sciences. It's a very difficult one, and yeah, we're not talking about hundreds of years at the moment. So in ARTEMIS, what we are doing or how we are structuring this is that we have a iterative design process that allows us that we are not static and that we are able to integrate innovation, we're able to integrate feedback and progress in the project. So when you look at this circle here, we've started on the very left with the plan and the outline. We went through a research and analysis phase in close collaboration with the other work packages, particularly with the communication work package, by creating a specific user survey. So starting off with the community and talking to the community, working on the structure of our platform, of our digital training platform, and further defining certain elements that we need for the training, like the user profiles, specific topics. And we're now down here, down on the right-hand side at the moment, because we have started a series of video lectures. We are currently working on a summer school, and whatever we do right now will feed back into the cycle. And towards the end of the project, we will try to come out of the cycle and move into the implement and deploy phase, where we have, hopefully, our final ARTEMIS curriculum that will be retained. And of course, this might not be the end point. When the next project comes up, this can further be developed. If particular groups want to do this, this is no issue at all. So far, what we've done is we've created core training topics. We have not created them, we have defined them. And they are based on what you have seen in the previous presentations. We have defined prospective end users for our training provision, which come from different backgrounds and have different skill sets. And that is a challenge in ARTEMIS because, as has been mentioned before, the cultural heritage sector is so diverse, and the skills of people are so diverse, and their needs are so diverse, that we need to try to address as many people as possible without becoming too generic and irrelevant. So it's a very small path that we're trying to navigate through. And we have key tools and services that also will be addressed in our training. What has happened so far is, for example, and I've just given you the titles here. You're very welcome to visit Daria campus and explore the resources yourself. 3, actually 4 of the people involved in the project have already created first video lectures, which are super short snippets that introduce you to some of the main topics that are covered in ARTEMIS. And it's really a starting point. As I said before, the end goal is an ARTEMIS curriculum that is more encompassing. This is our starting point. But we don't want to hold back until the end of the project. People need to see it now and get interested now and, you know, want to learn more. So that's why it's already here. And we, again, have to thank you, the communication workbench, for putting a lot of effort into this as well. Now, so we've started this, and we're currently in progress of creating a summer school next June. And of course, all of you are very welcome to join us there, to apply for it early next year. And yes, these campus resources are also part of it. And yes, the training provision will continue in the next year with more of the learning series, so we will cover more topics, go into more detail. We will have the summer school in June, which then will be a mix of theoretical information passed on, but also very real hands-on workshops. And you've seen my colleague Anesti's presentation just earlier with this amazing video where you can walk through the city of Scanzi without ever being there. So come to the summer school to find out what ARTEMIS can do for you. And we are also planning further on training events at respective partner universities who are part of the project to cover also a spatial wide range of people. So bring the training to the people. We have it online, but we also want to engage with our communities in person, in the spaces where they work and encounter challenges that ARTEMIS might be able to address. Thank you.
Thank you, Elizabeth. Do we have questions for the ARTEMIS training, I suppose? Not. Okay, we are getting later in the afternoon, but you were very, you also were very communicative, so thanks again. And now we pass the word to the communication team, so the last of the actions of ARTEMIS. So, take us to the next coffee break. Well, the floor is yours. By the way, I take this opportunity for thanking the communication people because they did incredible background work during these days of meeting and everything was quite good. So, thank you, Ginevra.
Bloccato il PowerPoint.
Forse devi pisciare di là. Non dovevi pisciare di là.
No, è bloccato.
Chiudi e riparte, via.
Potendo chiudere. Abbiamo Roald qui. Come le chiude?
Niente, non chiude niente.
Nel senso, la presentazione volevo farla ripartire, ma è bloccata questo PowerPoint.
PowerPoint è bloccato? Prova a ucciderlo.
E come lo uccidi?
Te lo dico io come.
Vai.
Ci vuole qualcosa di più cattivo.
Più cattivo, sì.
No communication from communication department.
Cioè controlla il lancio tipo.
Ci vuole qualcosa di più cattivo.
Dance.
Ecco, vai. Ok.
Coordinato.
Ora vediamo se parte, però.
Esatto.
Prima clicco enable content, forse. Ok. Ora va. Okay. Ora ve la metto
Okay. So, okay, we are ready. From vision to action isn't a slogan. It's the simplest way to describe what is really happening. Okay. In Artemis, a project that doesn't just imagine the future of digital cultural heritage, it's building it step by step. Over this month, we've turned a vision into a tangible milestone. We have clearly defined Artemis services. Thank you, Lucio. And we have built and consolidated the Artemis ontology, which provides a shared language to enable interoperability across data, methods, and tools. And we have defined all the pilots, as Anestis showed before. The point where ideas moved beyond theory and become real-world application. And if these achievements are evident on a technical and scientific side, they are equally visible in another dimension that matters greatly to us: communication and community impact. So, because today we can say within numbers to back it up that interest in Artemis is real. Our LinkedIn profile has passed 1,600 followers, and each post reaches on average more than 1,400 people. This matters for a simple reason. It shows Artemis is not a conversation happening only within the project. It's beginning, followed, discussed, and supported by people outside consortium. Yes. And we see that through message and comments that confirm the value of we are doing. Artemis is not just a research project, it's a movement. A clear example is Artemis Talks, a format designed to sit between a podcast and a video, something people can even follow while still making a complex topic accessible to a wider audience. We ran a first pilot episode, then a second, and the result exceeded expectation. Around 1,000 people connected at the same time to watch the latest episode. That's not just a number, it's evidence of attention, trust, and the project's ability to speak beyond its usual bubble. It's a movement.
Thank you, Ginevra. I would like to highlight a point that defines our mindset, because we don't stop with the number already good. In June, shortly before the Lecce event, we review our metrics that were really strong already, and we decided to rise the bar, estimating where we could be basically today, month 12, with a achievable and also challenging target. Today, I can say that the numbers are clear. We exceed 16K impressions, and we have more than 2,000 followers across all our social media platforms. But also our newsletter, also the visitor of our website are continuing to increase day by day. Let me talk about a little bit the learning series, because for me the learning series, for us, the learning series is a pathway that guide people to know Artemis and how to use his products and service. But we don't have to forget also that for us, the learning series, we have really strong impact into our community, but I would say also into the cultural heritage community in general. And the learning series is the natural step towards into the summer school, which we cover with the indicator and strategy and communication for our social media and also the website. Oh, wow. From vision to action. So, from vision to action for us is not just a catchy claim, okay? From vision to action for us represent 1 year of real impact, real milestone, real technical milestone, real impact into our community, and a concrete vision of what comes next. And I can say that let me see. Oh, no, that. Okay. Don't worry about that. I'm not finished yet. Okay. I'm not finished yet. So here we are. I think we covered a real nice year. We are concrete. We have real milestone, and I will say that we continue to have the same mindset as always. We stay hungry because this is how action is built. Now I finish. Thank you.
Thank you, Brian.
Thank you.
And next will be from action to reaction. What to say? We are at the end of the second satellite event of the first Artemis annual meeting. Well, 1 year has passed. We did a lot of work, but unfortunately we raised a lot of expectations. So the second year will be a test for everybody, including me. I'm still counting on a very strong group, a motivated group of partners. Now, after this meeting, I think the group of partners needs to be even more motivated because we are seeing which kind of results we are collecting, waiting to see what will be the outcome, the fallout of this morning session, which happened to be quite important for everybody. We will decide in the next weeks what line to keep and how to foster this cooperation that we kickstarted, voluntarily kickstarted, willingly and voluntarily and willingly kickstarted. What do you laugh? It's the reality. So, well, thank you again, everybody, and thank you again, Roald and the Kick, for hosting this beautiful event. Christmas is approaching. It's not even snowing in Brussels. What do you want more? So have a nice Christmas. Have nice holidays. Enjoy Brussels if you stay here tonight, or safe trip home. Thank you, everybody. Thank you.
Last year, we asked a simple question. What if heritage could think? What if it could anticipate change, warn us of risks, and help us protect what time has begun to forget? That question became our vision. And today, that vision is becoming action. In just 1 year, ARTEMIS has moved from concept to reality. Across Europe, researchers, museums, engineers, and heritage experts have built the foundations of something entirely new. A living ecosystem where knowledge connects, learns, and evolves. We created the ARTEMIS ontology, the mind of the reactive heritage digital twin. A shared language that unites centuries of history, science, materials, and context. A structure that allows machines not only to read, but to understand. For the first time, heritage knowledge can speak across systems, across disciplines, and across time. We designed the infrastructure that will carry this intelligence. We defined the services that transform data into foresight, simulations that test futures before they happen. And while the technology grows, so does the community behind it. Hundreds joined the ARTEMIS talks, opening a European conversation on the future of cultural heritage. Our first pilots are already taking form, from risk alert systems for national museums to new ways of planning, monitoring, simulating, and protecting what matters most. This is where the RHDT leaves the lab and enters the real world. From vision to action. This is ARTEMIS, a project bringing together knowledge, technology, and people to rethink how we protect, understand, and care for our cultural heritage.